Okay, it's 9.5, math induction. That's the new topic for today. And if I'm going to prove with math induction, I have to take a statement like this that they say is true. And by the way, we're not going to be evil and ever make you try to prove things that are not true and struggle with them all night. And we'll only give you things that are true. But we want you to prove they're true. So the simplest, the weakest kind of a proof is to just prove that if I stick in a number like n equals 1, that it'll work. So watch. I put in 1, and that means how many terms do I have if I stick in 1? N equals 1 implies there's how many terms? 1 term. Just 1 term. See, I know this confuses people. 2, 4, 6, 2n. What's going on there? It's a big list of, how would you describe those numbers? Even numbers. And do you get that we are actually adding them together? We're not just making a list of them. How can you tell we're adding them together? The little plus signs, okay? So what they're saying here is if you have a whole bunch of even numbers added up, how many are there? Well, you don't know until you stick in how many they're going to be. You pick that. I stuck in 1, and that means there would be only one number, and it would be 2 times 1. Did it spit out the right first number? Yeah, so it gave me a 2. Now, did it actually work? Is the sum of all those 1 numbers, did it actually work? When you actually do this, 1 plus 1 is 2. 2 times 1 is 2. So 2 is 2. It worked. I stuck in a 1, and it worked. I know this is a confusing way to see them because you're used to seeing them like this. You're used to that. And I'd say, okay, what did the first thing you'd put in? Hello? We put in 1. And then when I put in 1, you would get what? Negative 1. And then you'd stick in 2, and then you get another 1. Now, this is different. This is a big list of numbers being added, and that's not necessarily, well, the n is going to be the last term, and there could be terms in front of it. So let's do 4. Now think this through. If you put in 4, that implies there's how many terms? 4 terms. And what is the last of the 4 terms? Right here. Right here. It's 8. All right, so then it's 2, 4, 6, and 8. That's my list, right? What does 2 plus 4 plus 6 plus 8 actually make? Well, 8 and the 2 makes 20. It adds up to 20, right? Is it working? That's 5 times 4. Ha! It works. I went overboard. I tested 2 spots. I tried 1 and I tried 4. So have I proved it? That's always going to work? No, I just proved it works with 1, and I proved it worked with 4. I didn't prove it works for everything. So that's where induction comes in. We've proved that it's true for 1. Now, I went overboard by proving 2 things. You don't have to do that. You just have to prove it's true for n equals 1. Then you have to prove that it's more generally true for a variable. So I'm going to go to the next step, which is you have to prove it's true when we change n to k. Write that down. First step, prove n equals 1 works. Second step, prove n equals k works. Now, if that doesn't bother you a little bit, it should. Did I just switch an n to a k? I mean, aren't I just going to have the exact, isn't this the exact same thing as it was before, except with a k there instead? Well, it's part of the process of induction. Induction is a way of proving things in math where you always prove this 3-step process. You prove it for a number. It doesn't have to be 1, but 1 is the easiest one. Then you prove that you can switch the variable. This is weak induction. If you were going to actually do math induction, it would take us like 5 days. You're going to be walking out of here after 1 day pretty much knowing the process. The algebra can be tricky, but if you're going to do strong induction, that would be a whole different thing. This is just a weak inductive proof. This is the weakness right there. That it's just so easy to say let n equals k and just say, well, see, I've proven that it works for a different variable now. You know what I'm saying? I just stuck a different variable in. That's all I did. Okay, so that's the weakness of this proof. But believe me, step 1 and step 2, it's so easy. Everybody gets that right on the test. You just stick a 1 in, see if it works. And we've told you, it always works. Okay, and then you stick a k in for n. Why a k? There's certain things that are kind of conventions in math. Like for instance, if I'm doing slope, what letter am I going to use? M. If I'm doing the number 3.14, what letter am I always going to use? Pi, the Greek letter. And this, for induction, k is kind of the standard. All right. So all this is redoing this problem except sticking in n equals k. The last thing is, remember, these are always sequences where you have something bigger and something bigger and something bigger. What's bigger than k? K plus 1. So that's the third step, is to prove that this would also work for k plus 1. We let n equal k plus 1. And I'll show you that in the next couple slides. Yes? I gotcha. But 2k is the last one so far. Then we can go, if we want to go to k plus 1. And then what would be the next one after that? K plus 2. And I gotcha. I get what you're saying. You're saying, well, don't we want to stop this thing at some point? Yes. But we want to say, if we've proved that it's true, which was a weak proof, that it worked for k, now we have to do, and this is the tough part. This is not weak. This is the tough part. We got to prove that it also works for k plus 1. And we can't just go stick a k plus 1 everywhere. Like last time we just stuck in a k everywhere. This time, we can't just stick in a k plus 1 everywhere. All right. That's kind of a general overview of how these are done. Now I want to actually do one with you. So find this purple page. I'm going to pause for a second while I get something ready. Okay, so I just covered that up so that I have more room to work here. The n equals 1 step, super easy. I just stick a 1 in here, and that means there's only one term. And what would it add up to if there was only one term? Well, 1, 1. Figure that out, and I bet it added up to the right thing. 1 equals 1 times 1 plus 1 over 2. Big surprise. 1 equals 2 over 2. 1 equals 1. Hey, it worked. I proved it. For that I stick in 1 and it works. That little formula there is really the right sum formula for this situation. Do you remember it? It's start with 1, then add the biggest one on your list, and then multiply by n over 2. Doesn't that ring a bell? That's that formula, just written in a different way. And one that sums up all of the arithmetic terms. Okay, so now I'm going to prove it's true for k. Weak. I just stick k in for n. 1 plus 2 plus 3 plus ... k equals k times n, oh, not n, k plus 1 over 2. There. I already did the let n equal 1. Now here's the let n equal k step. Now here's the third step. Let n equal k plus 1. It's not as simple, I wish it was, as simple as just stick in a k plus 1 everywhere. You got to think this one through more. I'm going to recopy the original 1 plus 2 plus 3 plus ... k, and I'm going to leave myself some room to work. All I'm doing is copying with more room, that's all. Now, think about this. If I'm going to prove that this is also true for k plus 1, do you get that after the k term was done, we would add another term for the next one, which would be what? K plus 1. Instead of k, we'd have k plus 1. I've added so that my term used to go to here. All of them added up would be stopping right there. I got to add one more. Hey, I added it on at the end there. And if you add k plus 1 at the end of that one, do you get that this is an equation? And I can't just go around adding to the left side and not doing anything on the right side? That should be like adding k plus 1 to this side. Yes, sir. I didn't put it over k. You're right. There's no reason I would need to put it over k. You're right, and I'm going to in a moment. I'm glad you thought that. You'll see in a second. Do you get that the next one after k is k plus 1? Does that make sense to you? Okay. Do you get if I added something to the left side, then to keep it fair, I should add it to the right side? You with me so far? This is supposed to be the easy part. Okay, good. So now I have to take this and do a bunch of algebra to it to prove that it's coming out to the right thing. Well, what should it come out to? The goal here, and now listen to me carefully, the goal is to prove that by adding k plus 1, we'll get the same thing as if we had put in a k plus 1 here and a k plus 1 here. That's our goal. Our goal is to prove that when we add k plus 1, it'll be the same exact thing as if we had put a k plus 1 in for n. I know, it's tricky. But do you get up to here, up to this moment where we added k plus 1 to both sides? This wasn't too tough, but we have to prove that this gives you the same result as if you had replaced your k's with k plus 1s. All right, so what I do, and I think would work well for you, especially with the iPads that you guys use, is I write this out, and then you can circle it with that little lasso thing and then bring it down the page with you, because we're going to be doing one of those impressive problems where it might take us like 10 steps before we finally get to the answer. And if you don't drag it down with you, you won't even see what your goal is. So I'd write your goal out. I'm going to write it in blue here on the left side. K plus 1 instead of n. And instead of this n, here, actually I'm going to go like this. Do you get I just wrote the original thing here, except without n's? Now I'm going to drop in k plus 1s. I got to prove that this will come out to this. Oh, I need to get that grouped together. I'm going to pause for a second while I group it. Okay, so now getting this to this point is considered the point where you've gotten about half of the problem. You could get half credit at this point for knowing how to get your goal and how to, what the thing is that you added k plus 1 to. Now here's the algebra part. This is the fun part for me. It might not be as fun for you. It depends on your algebra skills. I've been working on those with you with that top 20. You should know a lot of these things. And I've been giving you a little tips on how to solve this all along. And we'll see if you recognize some of my tips that I've given you. All right, so somehow I got to get this right here. I got to get that to turn into that. What is the same about them? What does it have that's good? It's not exactly the same, but there are some similarities. They both have an over 2 in them. Okay, good. What else do they have that's similar? They have k plus 1s. They both have, in fact, they both have 2 k plus 1s in them. That's a good thing. So we are going to be adding these together and making them into one big fraction. Do you know why? Because this one's in one big fraction. We got to make them alike, right? So I'm going to take this and make it add together into one big fraction. So to do that, I need to have a common denominator, right? What's the denominator of this thing right now? I can put it over 1. How can I get it to have a right denominator? Multiply by 2. I'm going to times by 2 on both sides. Times by 2 here. And I'm going to times, notice me putting that in parentheses. That's a big deal. I can't just randomly times one of them by 2. The whole top has to be multiplied by 2. Would you please multiply that out and try to get this next step that's right here, right now. I told you what to do. Now you just try to do it. K times k plus 1 over 2, that didn't change. And I'm timesing the top and the bottom by 2. So this top became 2 times k plus 1 all over 2. So now all I did is basically rewrite this thing. Now I'm going to put them all together and put it all over 2 because they have a common denominator. So I was adding, right? And not over 22, it's all over 2. All I did was get a common denominator and put it all into one big fraction. I'll give you this hint. Usually, you're going to have to use common denominators. And then there's one more step that you usually have to do. Anybody look at this and see what I could do? Yes, sir? We are going to do what you just said, I can tell, but we're not doing it yet. Yes? I could multiply that out. That is not what I want to do. Do you remember my favorite saying? Yes? Yeah, you could multiply it all out, but you don't need to do that. What did I just say a second ago? Say that louder. Pull out, when you say pull out, what are you really saying? Factor out the k plus 1s. If you can factor it, you should. Once again, my favorite saying comes into play. And why is it my favorite saying? Because it's always the punchline to really hard math problems. You'll realize, oh, I can factor it. All right. What do you mean factor that out? Well, they both have a k plus 1 in them, so they come out to the front. And the k plus 1 is now out in front. And when you're doing that, you're really dividing this by k plus 1, and you're dividing that by k plus 1, and then the k plus 1's cancel, and then what do you have left? K plus 2. And it's all over 2. Now, have I got my goal? Is it equal to this yet? Oh, it's really close. Last part, you can just make one little substitution. What do you think we should replace with what? Yes, sir. I do need to get it exactly like it. Change this? I can't do that, just to clarify. That's my goal. I can't mess with my goal.
No, I mean, so you have k plus 2, you can do k plus 1.
Exactly. You can replace this k plus 2 with, do you get all I did is replace a 2 with a 1 plus 1? Wouldn't you agree that that can be defended mathematically, that you replace the 2 with a 1 plus 1? I mean, yeah, but it's true. Yeah, true, but you can't change your goal. Once you have your goal, you can't say, well, it's kind of like a person who's on a diet. Instead of like, I'm going to lose 50 pounds, it's going to be like, I'm going to lose 2 pounds, and that's good enough. That's cheating. You can't change your goal. Okay, we are really, really, really close, though. If I put these side by side, what's the only difference? And can I put in parentheses as long as it doesn't actually change the answer? Yes, I can, and that won't. So there we go. Done. That is your first math induction proof. You prove that it worked for 1. You prove that it can change the variable to k. That's kind of weak, and that's why this is weak induction. And then the last step is you got to prove that you could put in k plus 1. I'm going to show you again. Their goal was to prove that if you put k plus 1 here and here, that it would come out the same as adding k plus 1 at the end of this series right here. All right, so next problem. Find the one that's kind of a tan color, khaki color. All right, would you agree? Just use your brain and don't even write it on the paper. Would you agree that you can stick in 1? Let's make sure, double check it. Stick in 1 in your head. See if it actually works. Oh, and you need parentheses on this one. If you don't have parentheses around this 5 halves, I apologize. Put it in now. That's an oops. Because 5 halves, it implies the way it is that the n is being times by the 2. It's not. It's 5 halves times n times n plus 1. When you stuck in 1, did it work? When I stick in 1, this gives me 5. Is that the first term? Yup. And if there's only one term, then the answer should be 5. So let's see. Does this really give you 5 when you stick in 1? 2 times 1 is 2. All of that is 2. 5 over 2 times 2. 2's cancel. Would you agree? 5 does equal 5. Cool. I proved it. Works for 1. Okay. The next part is you got to generalize. So we turn it into a k. So that's, we just did n equals 1. Now we're doing n equals k. So I'm going to write it out. You have to. All you're doing is changing an n into a k. I understand that that's a little bit annoying, but all you have to do, nice simple step. There. Step 2, done. Step 3. If it works for k, then it also has to be able to work for the next one after k, which is k plus 1. So n equals k plus 1 is our third step and the toughest one. If you and a friend are doing these problems together, it'd be a great way to say, I'll do 2/3 of it. I'll do steps 1 and 2. You just do step 3. Okay. So if I'm going to put in k plus 1, 5 plus 10 plus 15 plus ... plus, a lot of people make the mistake of replacing the 5k. It's still in the lists. Do you get the k was the one before k plus 1? So now we're going to add another term and don't put k plus 1 here. How do you get the next term? You always take and do 5 times whatever that is. So it would be 5 times k plus 1. Just like this was 5 times k. Now we replace the k with a k plus 1. 5 times k plus 1. When I make a 15, did I like throw away the 10? See what I mean? It's just the one in front of it. We don't throw away the 10. The 10's just in front of it. Okay. Now that equals, I'm just copying now, 5 over 2 k, need parentheses here, times k plus 1. And then this is the part where you got to remember, if you added this to the left side, you also have to add it to the right side.
So how are we putting that k?
Hold on just a second. when you add something to the left side, it shouldn't be too much of a stretch to think that you'd add it to the right side. Okay, did you have a question? Yes.
So how in the previous one we had put n equals k, and you just put k in that.
Because there was only a k there.
So that's just 5 halves. No, we don't replace that k with a k plus 1. Like basic second route. How you had n equals k, and after the 5 halves, you have k.
After the 5, yeah. Yes, I got you. So far, I haven't touched this part at all. All I've done is add this to it. I didn't stick in k plus 1s yet. Do you get that the red underlines are identical right now? The red underlined parts are identical. All I did was add 5 parentheses k plus 1. All right. So now, this is where you got to figure out what's your goal. What's your goal here? Remember me saying that the goal is always to take this original and prove that adding this is the same as if you had put in an a k plus 1 there and there. So that's my goal. I'm going to write my goal statement over here. I'm going to replace my n with a k plus 1 and my other n with another k plus 1. That is this copied, except the n's are replaced with k plus 1s. That's how you find your goal. You take your original statement, you stick k plus 1s in it. Okay, so if that's our goal, I'm going to get that grouped so I can drag it down screen with me. That's my goal. I'm going to try to take this over here and do a whole bunch of work to it until it looks like my goal. So the first step on this is always to just kind of step back and look at it and say, what does it have in it that I want it to have in it? I want it to look like that. What's it got in it that's good? Got a 5 halves, that's a good thing. What else does it have? It's got a k plus 1, that's a good thing. What else? Does it have 2 k plus 1s? Yep. So it's got a lot of the right things, it's just it definitely doesn't look the same. So my first step on this one is I'm going to think through, what did Mr. Server say again about these? He said that we were going to probably have to do 2 things in them, usually. Ooh, factor. Is there something I could factor out of both parts? Do you get that on the left side? We can't even touch this thing, so we're not talking about factoring that. We're saying over here, do you get that there's a k plus 1 in both parts? Ha ha! Factor it out. If you can factor it, you should. So I'm going to get k plus 1 out front. I'm going to move this over so I have more room to work. I'm going to put it in parentheses. And then what's left over is a 5 halves k plus 5. I want you to digest that for a moment. I just took this and this out of it. I just divided that whole thing by k plus 1. And that made those k plus 1s disappear. And what I had left was this. Now I ask myself again. One thing that went bad is I don't have a k plus 1 anymore. I have one k plus 1, but I don't have another one. It's okay. It's actually still working. Do you get, I'd really like to get the 5 halves out to the front and factor it out also. I've already got the k plus 1 factored out to the front. That's good. Do you get, I also want to get the 5 halves factored out to the front. Do you see the 5 halves here? I can factor that out. But I think it would fry a lot of your brain. So I'm going to show you how to factor it out, and then I'm going to say, okay, Mr. Server, I could have never done that without you, so how could I have done it another way? So I'll show you another way. But here's how you could factor out the 5 halves. Just looking at this now, do you get that there's a 5 halves in the first part of it? So it's really easy. I pull that out, and I have k left, right? But really, when you're factoring something out, you're really dividing by it. So then it's really 5 divided by 5 halves, which if you flip and multiply, becomes 2. And why is k plus 2 good? Because it's the same as k plus 1 plus 1. You can factor out that 5 halves. And I understand that some of you aren't going to understand that. I think some of you got it. How many of you feel like you understand how I factored out that 5 halves? Okay, that's a lot of you. But if you didn't get that, and I'm going to just finish, for those of you that understood that, this is the final answer. I got to rearrange and move the 5 halves to the front like that one. So I'm moving 5 halves out front. Then k plus 1 next, just like it has it here. And then the last part is, since that's equal to 2, it's also equal to k plus 1 plus 1. And then I can just throw in an extra parentheses, and it's now identical to my goal. But if you're not buying that because you're like, I would have never known how to factor that 5 halves out, then at least you could do this. You could say, okay, well, I guess I could try getting a common denominator, because that's one of the things Mr. Server said, right? Common denominator here would make this need to be a 2. You know where I'm going here? Times 2 times 2. This will become 5k over 2 plus 10 over 2. And that makes 5k plus 10 over 2. Now can you see how to take the 5 over 2 out? I'm going to take the 5 out of the top. Anybody in here could have factored that 5 out. And now do you see that the 5 over 2 is out?
You can do multiply.
Yeah.
I don't remember ever saying multiply by 2, but anyway, 5 over 2 times k plus 2. And then this part we never messed with was k plus 1. I'm just showing you an alternate way we could have done it. But that, now I just have to rearrange. 5 over 2's first, k plus 1 second, and then the last thing is this k plus 2, which I'm going to just do it all in one step. K plus 2 is the same as k plus 1 plus 1, and then I can throw in parentheses. And there we go. Our goal was that. It's now equal to that. Intense, I know. Most intense thing of the semester. Congratulations, you just made it through the hardest day of the semester. There'll be another hardest day of next semester too, but this is the hardest day of this semester. Well, it should be at the end, shouldn't it? You don't hit with the hardest thing on day 2. You guys would all quit.
Can we do it?
Yes.
I'll try to put the 5.
Sometimes I just feel like
Nope, because I don't have time. But I can start your homework with you, which I think will help you more. Okay? All right. Everybody find the homework, which says right here, assignment day 1. Get there, get there, get there. See it? We're pressed for time, so I got to keep moving. All right, so first of all, you'll notice it's problem 1 and problem 2, but there really isn't because you're not doing problem 2. We're only doing one problem tonight, and that's this one. Good. So the easy part is, well, what's the first step? And it is easy. What do? Prove n equals 1 works. Go ahead, stick in n equals 1. When I stick in n equals 1, I kind of find out 2 things. First of all, that when I put in a 1, it comes out to 3 minus 2, which is 1. And it's supposed to generate the first term, and it did. Yay, there's only one term, and it's 1. Now we stick in a 1 over here, and a 1 over here. And this becomes 1/2 times 3 minus 1, which is 1/2 times 2, which is 1. 1 equals 1. I proved it. N equals 1 worked. Check mark. What's the second step? N equals K. And isn't that pretty much just copying? Hey, just copy it down with a K in it.
You don't have to.
Yes, there's no K's in it in the first place. There's only N's. I'm replacing all the N's with K's. That's what we're doing. All the N's are now K's. There. All I did is copy it and put in N's or K's instead of N's. That's step 2. So if we've now switched it to a variable, now we got to do the one after that. But we aren't going to be dumb and change letters. We're going to say what's after K? N equals K plus 1. So now we write this out. I'm doing your homework for you. I would recommend joining with me here. Why did I write all of that? Aren't I going to replace that? Nope, I'm not. Just like I don't replace the 4 when I make the next term of 7, I leave the 4 in the list. That's all there, and I got a new last term, and it's 1 bigger than that. So I take this, 3K minus 2, and instead of K, I put what? K plus 1. And all I'm doing is copying this down right here. But wait, I just added a term to the left side. So to be fair, I do what? Add it to the right side. I'll do that in red. Plus 3K plus 1 plus 2. Minus 2, sorry. Need a lot of room for these problems. Now, we're going to do a bunch of work on this. And eventually, we got to know what our goal is, right? Who remembers where you get the goal from? The original, right here. And you put in K plus 1 here and there. And that will become your goal. You're going to try to make it look like that. I leave you with the algebra, which I know is not easy. But if you look at it for 1 minute and then go, I'm looking at the key, that will not help you because the test is going to be a challenge. Struggle with it. Look for opportunities to factor and get common denominators. And that's all I got for you for today.